We're going to take a look here at a reaction in organic chemistry called substitution. It's when one atom replaces another atom in a compound, just like it sounds. We're going to be looking at the substitution of halogens, fluorine, chlorine, bromine, iodine, and how they can replace hydrogen to form what we call alkyl halides. This was one of those things that was up front in my classroom. Or halogenated hydrocarbons is another word for those. Heat or light is needed for this activation. We don't really go through the mechanisms in this class, but you can look into them if you want. Here is how it works. You've got chlorine. Chlorine is diatomic, so that's why it's written here as two chlorines. And one of the chlorines is going to replace one of those hydrogens. At this case, it doesn't matter which one it replaces because all of these hydrogens are equal, which is why in this case, we're only going to get one product that's made. So the chlorine attaches and the hydrogen comes off and attaches to the other chlorine. So your product is going to be a mono-substituted alkyl halide as well as hydrochloric acid. Here is an example where we're getting more than one isomer that's formed. This is the mono, meaning one, chlorination, meaning we're adding chlorine, the monochlorination of butane. So we have butane, and butane again reacts with chlorine. There are two of them because it's diatomic. And the chlorine attaches in where one of these hydrogens go. Now, since just one chlorine attaches in, it's going to produce two products. We're going to end up with one chlorobutane, which is attached to chlorine or carbon number one. We're also going to get two chlorobutane. Now, the reason we don't get three chlorobutane is because three chlorobutane would be exactly the same as two chlorobutane. There's also going to be hydrochloric acid, don't forget about. So this particular example produces two isomers, but you can see where it might produce a lot more than that. Continuing to look at substitution here, if you've got excess halogen that's present, that means that if I add more than 1 mole, the reaction produces what we call poly or many halogenated products. So if you've got 1 mole of chlorine, you produce chloromethane. If you add more, if you add 2 moles, you're going to get dichloro. 3 moles will give you trichloro, and 4 moles will give you tetrachloromethane. It's also important to remember that the more chlorine that you add, 2 or more moles, you're going to get 2 or more moles of hydrochloric acid that's going to be formed along with that. So scientists can actually control the reaction conditions to favor one of these products if this is what they're looking for. So what are halogenated hydrocarbons that you might encounter? Hopefully this isn't one that you're going to encounter, but one that has an interesting history is chloroform. This is the one that you think about like spy movies or something where they put it on a little washcloth and they put it over someone's face and then they pass out. I think a more interesting history is that it was formerly an anesthetic, and so they used to use it. Not only was it not good for the patient because it was a possible carcinogen and they could die, but also some would leak out, and the doctors used to get some chloroform, and once in a while they would pass out during the surgery. So that's interesting. Carbon tetrachloride, which was another one from that page, is formerly a treatment for hookworms and also causes kidney, liver disease and is a possible carcinogen. Looking on, we've got freons. Someone might have done their project on this in your class. I'm going to let this video tell you a little bit more about freons and their important history.
Air conditioning, as well as refrigeration, which is the same thing, just in a slightly smaller box, relies on the laws of physical chemistry. And PChem tells us that as a liquid evaporates into a gas, it absorbs heat. The molecules in a liquid are held together by weak intermolecular interactions. Not quite chemical bonds, just enough passing attraction to keep them from flying apart. Some of the molecules absorb enough heat energy, in other words, they get moving fast enough, to overcome these intermolecular attractions, escape, and take gaseous form. That's the reason you feel chilly getting out of the shower, and why we sweat to stay cool. The water has to absorb heat to evaporate, and it carries that heat away from you. An air conditioner's basic job then is to use a fluid called a refrigerant that constantly changes from a liquid to a gas and back to a liquid again to move heat from one place, like your sweaty bedroom, to another, outside, where it's already hot and miserable anyway, so who cares? Here's a admittedly very schematified version of how most AC units work. The liquid refrigerant flows through a series of coils exposed to the air in your home. The refrigerant has a low boiling point, so the heat from the interior air is enough to make it turn into a gas, which means there's now more heat in the refrigerant and less in the air. A fan blows that colder air into your room, or straight into your face. We're not judging. So now your AC has to do two things. Dump the heat absorbed by the refrigerant outside, and two, it has to condense the refrigerant back into a liquid so it can be used again. And to do those things, it uses a compressor to ramp up the pressure on the gaseous refrigerant, so much that it can condense into a liquid again, even though it's at the warmer outside temperature. As it condenses, the refrigerant loses heat to the air around it, which another fan blows outside where it's already all sticky anyway. Which is a neat trick, boiling something at a low temperature and then condensing it at a high one. Nothing in thermodynamics is free, and the compressor needs energy to do the work of compressing the refrigerant, which may explain your power bill in July. After the refrigerant condenses, the air conditioner backs off the pressure with an expansion valve so that the refrigerant can boil at the lower temperature again, which it does, in a loop, over and over, until your home reaches the temperature you set the thermostat to, or your housemates complain and switch it off because what are you, a polar bear or something? Jeez. While the refrigerant could be practically any substance, there are some chemicals that do the job better than others, and these refrigerants have a checkered history. A refrigerant needs to have a pretty low boiling point, and one that can be adjusted to where you want it by changing the pressure on it. It should also be pretty good at conducting heat and be able to absorb a lot of heat as it boils. And then it needs to be cheap, widely available, and as non-flammable and non-toxic as possible. That all kinda narrows your choices of chemical. Scientists thought they'd found the perfect refrigerant with Freon, which is the trade name of a group of chemicals called chlorofluorocarbons. But CFCs are actual murder to the ozone layer. They've been largely replaced with hydrofluorocarbons, or HFCs. HFCs don't damage the ozone layer, which is good, but they have a different problem. They're greenhouse gases. So the search is on to phase out HFCs too. Some alternatives? Simple hydrocarbons like these have been approved in the USA. Hydrofluoroolefins like this one are less rough on the climate than HFCs, but also more expensive. The most surprising potential replacement is CO2. CO2 totally works as a refrigerant, and even though it's the literal poster child for greenhouse gases, it's also way less potent than HFCs. Whatever we use in the future, it doesn't seem likely that we'll give up on AC altogether. Not in a scorching summer like this one. Pass the popsicles, would ya?
Halogenated hydrocarbon that has a kind of a bad history would be ethyl chloride. They used to spray it on as an anesthetic. It worked like icy hot, just like the video just said. It had high volatility and rapid evaporation, and then you lost heat from the surface of your skin. So this is how icy hot works. DDT is the last halogenated hydrocarbon that I want to tell you about. It was used to kill mosquitoes and pests, and it was used during World War II a ton. This is when it came out, and they thought it was really safe. And there's even videos of like scientists taking baths in DDT on how safe it was for humans. So it was used in agriculture as a mosquito killer. But then what they found out was that even though it wasn't too bad for humans, and it turns out it's not real great for humans anyways, it is not biodegradable and it is very stable. So what it was doing was it was building up in the fatty tissue of animals, and they would eat other animals, and then those animals would eat other animals, and it goes up the food chain. We call this biomagnification. So this is why you've probably heard about this in your biology class. And then it really hit the predatory birds, and it softened their eggshells, and birds were dying. And this was the first time that something was called out by an environmentalist. And in this case, it was Rachel Carson, and she wrote the book called Silent Spring that called out DDT and pretty much changed the history of environmental pollutants from then on. DDT has been banned in the United States, but interestingly enough, it is still used in other countries because since it kills mosquitoes really well, it can help to fight malaria. And even though it is not good for the environment and not really great for people, it's not as bad as malaria. So I'd like to move away from alkanes to finally talk to you about alkenes. Remember, alkenes are hydrocarbons with at least one carbon to carbon double bond. They can be open chain or cyclic, like alkanes. Four or fewer are gases, and five or higher are liquids. So that would be butene, or fewer would be gases, or pentene or higher would be liquids. They are also less dense with water and they are not very soluble in it. So you can see here is ethane, and with the double bond right here, we call this ethene. Alkenes are really important starting products for polymers. Okay, so the need for them, because obviously we have a lot of polymers out there, polymers are plastics, exceed their natural occurrence by a lot. So they are produced during cracking. And if you don't remember what cracking is, go back to the beginning of your notes, rewatch a video or two if you have to, because this is a really, really important part of this chapter. 50% of the 400 billion pounds of organic chemicals use ethene, or the old name ethylene, as a starting raw product. And again, this is because it's what's used in polymers. And if it's not ethylene, it's something really close to ethylene that produces all of these products that we see. Alkynes, not as important, but those would be unsaturated hydrocarbons with triple bonds, okay? Looking at these bonds again, I know we went through this rather quickly, but they basically have one sigma bond and two pi bonds. If you're looking at the bonds in an alkene, they have one sigma bond and one pi bond. When you look at these pi bonds, they go above and below the internuclear axis, so they form above and below. What this makes happen is that there is no rotation around this carbon to carbon double bond, which is why they produce this linear molecule here. Alkynes have names that end in "ine." An alkyne that's kind of interesting would be cutting torch gas, which I'll show you a video of. Also, propane is another one, and people have been talking about using this as fuel for rockets or spacecraft because they have so much energy.
What we're going to do is we're going to turn our acetylene on first. Now, acetylene is it's kind of what you think of as the fuel gas. This is what's burning, right? So the fuel gas you're going to turn on first, just kind of maybe like a quarter of a turn there. Get your starter. Now you can use a little starter like this, or you can use a lighter, whatever you have available. So you're going to get that started. Now you want to adjust, and the first thing you'll notice is you'll probably see some black smoke coming up, right? You see some smoke. Now if the less acetylene you have coming out, the more of that black smoke you have coming out. Now what you want to do is adjust your flame until that smoke is going away pretty much, right? And you can see the flame is starting to feather off a little bit too. So we're going to adjust that up a little bit, and you're still going to have a little bit of smoke. And then you're going to turn your oxygen on. We're going to adjust the amount of oxygen that we have coming out. And we're going to do that with this top knob. So we're just going to turn this slightly. And you can see your flame starting to change. And you can see it's starting to change at that tip. We're changing color. We've got all these little spikes here, nice clean spikes. Some people call them flame cones. I call them spikes. You can call them whatever you want to. But you see they're nice, clean spikes there. And that is what you want. So you're going to maintain a nice even pace all the way down your material where you're cutting and keeping the trigger squeezed. So you're just going to be forcing through. Now you think of it as pushing this puddle. You're going to take that heat and you're just pushing that heat, keeping it in front of your cut all the way down. You want to keep everything in front of that cut hot so that gas that's pushing forward can push through that heat. Because if it's not hot enough, it's not gonna cut. It's just gonna blow back.